There we go. Okay, good. Please.
Okay. First, thank Mel to invite me give a talk in this seminar. Actually, I heard this seminar many years. So, but I'm glad to give a talk here because most time I'm working on the dynamical systems, but recently I got some interesting on this problem, which in number theory. So I mute myself. Sorry, can you hear me now, right?
Yeah.
Okay. So first, thanks Mel to invite me and give a talk in this seminar. I heard this seminar, many years ago. Also, I'm glad to join this seminar. Most time before I work in this complex dynamics and dynamical systems, but recently, just the past few years, I just got interested on this problem in number theory, then try to combine the ergodic theory and the number theory. So since I'm still learning a lot of things in number theory, so I hope if I have a question later, I can ask you guys, right? So that's nice to give a talk here, then get acquaintance with you. So first, my title is Ergodic theory motivated by Sarnak conjecture in number theory. So let me start from some function called a Mobius function. I think everybody here probably know that function is, right? So that is an arithmetic function on the natural numbers. So which equals 1 if n equals 1, and minus 1 to the r if n can be factorized into are different prime numbers. So if n has a prime square, right, square of a prime as a factor, then take 0. So right, so that is a picture, a graph. I actually you can see a little bit about how this value distributed on the plane, right? So that is called a Mobius function, which is okay. First, I think very basic property about this Mobius function is that is multiplicative, right? So that means the value on the n times m equals value on n and m as long as the n and m are relative prime, right? So that is one thing. Okay. So another thing is this Mobius function can be written as a root of unity, right? Can be written as a root of unity for all the k, which is relative prime to n, right? Then also, if you sum the value of this Mobius function on the factors of n, then if n equals 1, that's 1. Otherwise, it's all the 0. So that is another interesting property. But another property, which called the inversion property, that's actually first time, long time ago, I got interested on this inversion property. The reason is at that time, I tried to start a so-called dynamical zeta function. So then I need to use this inversion function. So what does that inversion means? If you write alpha n are two arithmetic function, right? Arithmetic function, then alpha n can be written as summation of beta on all the factors of n. Then you can inverse this beta n, write as a summation of factor on n and Mobius function time and alpha. So for example, why I got interested in that, for example, if I have a flow, which usually we also call the dynamical system, right? You see, that means you have a function, right? You have a function which is from a space to space, then you to iterate it, then you get a flow, right? Or we call dynamic system. Then you are interested in what is a periodic point of period n. Also, you know what is a fixed point of f to the n. So then here I write alpha n as number of a fixed point for f to the power n to the n. that means all the fixed point, which is you apply f n, then that are fixed. Then those numbers are easy to calculate. But then periodic point of period n is that means n they repeat returned. But meanwhile, they are not repeat. So that is, you see that, right? Like just like here. So that's fn minus 1 of x, right? So then you see if that x is a periodic point of period d is a factor of n, then that also counted here, right? Count here, but not count here. So then usually these alpha n are easy to calculate, but beta n is not. So now you can use this inversion formula. You can just calculate the beta n. But most time when we study this so-called dynamical zeta function, we need to put a beta n into this formula. So that is the first time actually I really use this Mobius function in my study. So now let's see, then some deeper relation of this Mobius function definitely is with so-called Riemann Zeta function, right? So this formula actually is true for all the s bigger than 1, right? So, but this one is defined on how the complex plane accepts some point. But so this is called a Riemann Zeta function. Everybody here, I think, know these functions, right? So then you consider the one of a Riemann Zeta function, then you will involve this Mobius function. Another statement, actually that statement or conjecture, whatever you want to say, is that for every epsilon bigger than 0, then summation of this mu n has order n to the power half plus epsilon. That's really equivalent to the Riemann hypothesis. So that's all the thing from number theory. So then another important number theory property about this Mobius function is the Mobius function has 0 mean. So usually if you think that is really mean equals 0. So that has a 0 mean. But this 0 mean also equivalent to the prime number theory, right? So this prime number theorem said all the prime number is less than equal than x, which approximately x plus log x, right? But actually they have some error part. Also is interesting to study. In particular, in dynamical system, when you study this, you count periodic orbits, you have a similar result, but you need to estimate this error part, right? So that is another important property about this Mobius function. So now I'm going to talk everything is in number theory, but let's talk a little bit about dynamics, right? So first, how can you view this Mobius function in the dynamics? So first, you consider since the Mobius function takes 3 values, -1, 0, 1. Then you just take this set with a discrete topology. Then you product together, get an infinite product. Then you every element can be write as infinite string of -1s, 0s, and 1s, right? So then this we call the sigma 3, capital sigma 3. That is with so-called product topology. That will be a compact metric space, right? That's a compact metric space. Then on this space, you have an interesting map which called a shift. What is shift? Shift means you give any point, you just knock out the first letter, right? You get a J2, JN, right? You knock off first digit, then you got shift. That's shift is actually in this case a 3-to-1 map, right? It's not a invertible, but it's a 3-to-1. Then if you look at this Mobius function, really you think this Mobius function is a point in the sigma 3, right? Sigma 3. Then you can start iterating, right? You can iterate this one. Then you iterate it and take a closure. That will be form a compact. So this is a compact set, right? compact subset. Compact subset. And sigma 3 also map this lambda into itself. So this one, you form a so-called sub dynamic system, right? This is a sub dynamic system of this one. So then this question is that a Mobius flow? Mobius flow is simpler or complicated, right? But definitely we expect that's complicated. Otherwise, that's maybe easier to study. But how do you say this one is complicated? So then in dynamical system, there is a number, the quantity called entropy. So called entropy. So this entropy associated with any dynamic system, or we call the flow, right? In this talk, I like to call the flow. But in dynamic system talk, usually they don't like to call the flow. They want to call dynamic system. So then, for every dynamic system or any flow, you will associate with a number which is called entropy. So this entropy is a very important invariant in this subject. That is a topological invariant. But I'm not going to give you the detailed definition of this entropy because then you need a lot of things to say. But I just want to say this entropy is very important quantity in the dynamic system, which is measure how dynamic system can be, how complicated this dynamic system can be, right? So so now you can just say you want to see this Mobius flow is simple or complicated. You can just measure this entropy, right? So how do you measure the entropy? For Mobius flow, you have 3 letters. Sometimes it's not very easy to calculate this entropy, but somehow you can project sigma 3 into sigma 2. Sigma 2 will be 2 digits, only 0, 1. You also take infinite product. That's again is compact metric space. And you also have a shift. This we call sigma 2, small sigma 2. That also means not the first digit, right? So now then you can project sigma 3 into the sigma 2 by iota, right? Then what do you mean project? That means you take every digit by square, right? Then if you take everything is square, then it becomes 0, 1, 0, 1, right? So then this Mobius function project to the sigma 2 will records all the so-called square-free natural numbers. That means all the integer which has no square prime as a factor. So then in number theory, there's another interesting result that this square-free number occupied density, which called density 6 over pi squared, right? Then you can see that this sigma 2 restrict on this space, right? So you project that one, you also project this lambda to the iota lambda, right? Then you have a lambda to the lambda, you have sigma 3. Then you project to iota lambda. Then you have a iota lambda. So that's sigma 2. So that's a project. So this project is onto, right? It's not 1-to-1, it's onto. But then you see this one, if it is something called a factor of this one. So since this one has entropy is 6 over pi squared log 2, then that implies this one is bigger than this number. So entropy is positive. So since the entropy is positive, that means this dynamical system is complicated, also random, right? So that is the way you can view from dynamics about this Mobius function. So then this Mobius function is not a view as dynamics is complicated, but also have a lot of so-called oscillation. If you look at the graph or picture I just show you in the very beginning, first page, you see they actually have a lot of oscillator, right? So up or down, up or down, up or down, right? So so that means in the 37, right, the Davenport actually prove this theorem. So that's that Morpheus function actually, that really means the mean of Morpheus function time 2 pi I theta. So this one also have 0. Not only Morpheus function itself has mean 0, but if you couple with another function, so this one. So now, so that is a Davenport theorem. But how do you view this one in dynamic system? So if you look at this one, this map. So this map is so-called rigid rotation on the circle, on the unit circle, right? So you have a 1, then your rigid rotation, that's theta, right? That angle is theta. So you keep it rotated, right? So if you iterate this one, you actually get a keep it rotated like this. So then that really means if you rewrite this one as this form, that means mu n and this dynamical system of flow is so-called linearly disjoint, right? Orthogonal, but it's mean orthogonal. You have divided by n. So that is actually true for all the theta. For theta equals 0, that's just prime number theory. So if theta, for example, equals half, then you can see this summation divided into 2 parts, right? 2 parts. If theta is like a P over Q, then you divide a Q different summations, right? So in particular, is theta is irrational. Let we see later. So that is, theta is irrational, then this orbit is dense. Actually, not only dense, also equal distributed on the circle. But then this sigma mu is always still have a mean 0. So here's I want to talk a little bit about this dynamic of rigid rotation. So first, this flow of rigid rotation has 0 entropy. I'm talking about topological entropy, right? 0 entropy. Another thing is this one is so-called equicontinuous. I think if you know what is equicontinuous, that's fine. But later I will just give you a different definition, right? So then if theta is rational, right? P and Q are relative prime, then this orbit is just like this. You have 0, 1, right? If you can think a circle as 0, 1, then include 0, 1, right? So now you cut this one into the Q, different equal sized subinterval. Then the map is going to here, so that is P. Then next time you go to another P, right? Here's another P, there's 2P. And keep doing, you apply Q times, that come back. So that means that will be is a periodic function. That means R theta to the Q, iterate the Q times will be returned to the identity. So if theta is irrational number, then this one is actually dense on the Hollow interval, on the circle, right? It's dense. That's not only dense, but it's also so-called uniquely ergodic, actually respect to the Lebesgue measure, right? The probability Lebesgue measure, or had a higher measure. So that is actually unique ergodic. Another thing is actually is eco-distributed. So that's also is from a theorem in the number theory in the 1910. That means n theta model 1. This one is actually eco-distributed on 0, 1, right? So if the theta is irrational, right? So so how do you see this this one in dynamics? Actually, you see that if you have this 0, 1, then right, then if theta equals p, theta is irrational, then you can see that the orbit will be like this. Then come here. The another periodical, so then you leave the something here. The next one is come here. Since the model 1 is come to here. Then you keep doing like this. Then you get that one cut. So then more and more dense, actually, you see that's actually eco-distributed. Right, from dynamics point of view, that's the way you can just see how wide is eco-distributed on the 0, 1. So that is the Dynamics Davenport theorem really is so we call the linearly disjoint with so that means this dynamic system which linearly disjoint with this Morphius function. Right. So then Sarnak make a conjecture back to the, maybe a few years ago. He said that, okay, so this thing is not only true for this circle ridge rotation, but actually should be true for every flow which has entropy 0, has a 0 entropy, So now that's that. Suppose F is a flow, right? So that means F is a map from X to X. Then you iterate it, right? You get X to X. So then you get a flow on compact metric space. Usually we think about a continuous flow, right? Then for any complex valued continuous function, then any X, then this Morphius function is linearly disjoint with this observation. I'm going to talk about observation later. So that means this limit is actually equals 0 for every point, every continuous function, right? Every point and the orbit. Then you put on the continuous function, and they will have this one. So that is basically that conjecture. But I'm writing into a very general version. But
there's something. Isn't there some assumption missing here? I mean, the phi function, don't you have to have some requirement on it?
Yeah, I said it's I want is a continuous, right? That's continuous. Actually, piecewise continuous. I really do not want to very specify piecewise continuous, right? Okay. So X is a compact metric space. F is a piecewise continuous function, and you want this one to happen. Or you can assume F is a smooth, it doesn't matter. Yeah. Okay. Any more questions? Okay, now I'm going to continue, right? So now I say, so first, what do we mean flow is echo-continuous? Echo-continuous means for every epsilon bigger than 0, then you can find the delta. As long as the xy is less than delta, then all the orbit will be less than epsilon. So that is in dynamic system. This one also called something called not sensitive to the initial condition. That means if you have a 2 point which is close together, then the orbit doesn't matter how far they go, they also close together. So usually a flow or dynamic system is sensitive to the initial condition. That means if you have 2 points very close, but its orbit eventually will be away, right? That means it doesn't matter how you 2 points close, then your orbit eventually will far away. This is called sensitive to the initial condition. But echo-continuous means they are not sensitive to the initial condition. Another word, from some point of view, this dynamic system is relatively simpler. Why is that the relatively simpler means I need to put a quotation on that because they still could be complicated, right? So, for example, in the circle, irrational circle map, that's a unique ergodic, also echo-distributed, even that is echo-continuous, right? So, but anyway, so then Sarnak conjecture holds for all the echo-continuous flow. That's actually when he can make a conjecture, he already see that. So, for example, what is echo-continuous flow? So, for example, the simplest one we can see is if you give all any orientation preserving circle homomorphism, right? If you let's come back to circle again. So F is homomorphism on the circle. Then every such homomorphism has something called a rotation number. Then we assume this rotation number is irrational. Then this F is equicontinuous if and only if it is topologically conjugated to the rigid rotation. That means, so that's T to the T, you have F, but then you have another homeo, which is map T to T. So, but here's a rigid rotation. So this is diagram commute. So that means basically, that it means this F except some homomorphism change of coordinates that actually is just like a rigid rotation. Okay, so so then you can show this circle map is equicontinuous if and only if it is topologically conjugate to the rigid rotation. Then from this point of view, you see, then this one on the equicontinuous more general version of this Davenport theorem, right? More general version of the Davenport theorem. Definitely, you have a lot of equicontinuous map, right? I think, well, but equicontinuous a lot. Not only circle homomorphism, you have many equicontinuous map. So, but the equicontinuous map definitely has a zero entropy, right? So that is one thing. But then you ask, so okay, how do you have a map which is not equicontinuous but still have a zero entropy? Well, that's one easy to construct. So that is non-equicontinuous circle homomorphism, still circle homomorphism, right? So here's the way you construct that. So I wrote it here, but let me just show you how to construct that. Not difficult to construct. So now you take a circle, right? Then you take one here, right? That's circle on the complex plane. Then you consider rigid rotation R theta. Theta is irrational. Then you look at you iterate, you get a orbit. That's actually a lot of point on the circle, right? It's a iterator. So now you just open up this every point to an interval, right? Open up every point to an interval. So that's IN. So then that is, let's say, is IN plus 1, right? You open up as an interval. Then you just connect it. So that is just assume this summation of the interval is less than equal than 1, right? Then you reconstruct the circle, right? If you just connect all the intervals, you basically reconstruct the circle. But then you normalize still the unit circle, right? Still unit circle, right? You normalize. So then you define this F on each circle from Fn to the n plus 1, just like a linear map, but increasing, right? But still map endpoints to endpoints. Then you, on the complement, you define just like R theta. So this map is actually not topologically conjugated to the rigid rotation. Also, that is not sensitive to the initial condition, because if you take any 2 point close, then eventually they will, if you consider, if for example, you take any point here, then eventually they will cross this I1, because all the interval will preserve, then the distance will be bigger than equal than some given number. So this one is in dynamic system we call the Dandroit counterexample. So this one is you just start from rigid rotation, you just open up every point on the orbit into interval, then you construct the homomorphism. Then that one will not be equicontinuous, but still have entropy 0, right? This one, the entropy is still 0, right? Entropy, which we use H to mean entropy H is still 0, right? So that is example of a non-equicontinuous circle homomorphism with entropy 0, right? So now you want to see how this Sarnak conjecture works for this one or not, right? So actually, many people started that one. Actually, that's right, right? But so now what is our purpose actually? So we would like to understand this oscillating property presented in the Mobius function, right? As I just said, Mobius function has some kind of oscillating property, but not only that one, they actually have a lot of different version of this oscillating. Also, Mobius function have actually. So also some other arithmetic function. Also, we want to also classify all the zero entropy flow such that the linear disjointness happen in ergodic theorem. And also we can possibly we want to apply back this one to the number theory, right? So that's basically what my purpose into this study. Okay. Okay. Any questions? Right.
How much of this depends upon the primes? In other words, the Mobius function maps to -1, 0, 1. It's oscillating. It has certain properties. Are there other functions that have nothing to do with the primes that look just like that? And would that give insight?
Yeah, that's what I'm trying to get into. I'm trying to get a more oscillating sequence. That's what I try to study, actually. Thank you for asking that question. Yeah. Okay.
I had one other question. I don't know if you can answer it. Can you give me an intuition what a zero entropy flow looks like?
Okay, a zero entropy flow. Okay, I have a lot of example later. So zero entropy flow, from dynamic systems point of view, is supposed to be very simpler, because if you have a positive entropy, usually means very complicated, right? But point is a zero entropy flow also is also rich supplied. They have many different phenomena happen there. For example, circle is one. This another one is called adding machine. I'm going to talk about later. Also have a torus map, also high dimension. You know, the many different version of the zero entropy flow. Okay.
Any factor closed language which has very slow growth will give a zero entropy shift, right?
Right. You have some kind of slow growth, right? Usually you have exponential growth, then you have positive entropy. You have some kind of polynomial growth, you have a zero entropy. Okay. Yeah. Who is that answer that question? That's good. Thank you. Right. So really zero entropy means how these things grew. Its growth is exponential. That's positive entropy. Its growth is like a sub exponential, that it will be zero. Also polynomial, you know, they have a polynomial degree 1, polynomial degree 2, polynomial degree n, or sub exponential. All these zero entropy, but they are different. Okay, good. Okay, so now I'm going to come back to the ergodic theory a little bit, right? So now I'm said, okay, Mobius function is one function in the number theory, but I want to see we have other kind of sequence of a complex number also have a share same property like a Mobius function, right? Then we back to the Mobius function, right, to understand the Mobius function. So now let's see, suppose I give a sequence of complex numbers. So we see this complex number is so-called log uniformly oscillating. If they are two constant A, B, such that this, when you put a test function, E2 pi n theta, joined with Cm, then for summation to n to the capital N, you take a supreme, that one is less than this number, right? So that's basically follow from number theory, right? For this Mobius function or other dual function or some other functions. So then, but here I need something called a control condition. This control condition is that that really is a technical condition, but said this Cn will not be too big, right? So so then you can see that definitely this Mobius function is one example of this log uniform oscillating sequence by Davenport's result, right? Then you can easily, not very easy, but I mean, you can prove ergodic theory. That's basically in the Sarnak lecture notes has for the Mobius function. I try to get a more general sequence so that, okay, suppose you have a Borel probability measurable space and F is automorphism, that means F is 1-to-1 and onto in measure sense, So then suppose this Cn is a log uniform sequence. Then for every L1 function, you can have something like this. This one is tends to 0. That's the Cn coupled with this phi of Fn. Actually, you can see that Fn. That is, but AE in X. But usually in the ergodic theory, as long as you get the result AE, everybody will be happy, right? So, but in number theory, I think you really don't want the AE, you want every point, right? You want every point. So that is said, okay, you really want to improve this one to the every point. Right, every point. So you want to improve, right? Improve to every point, right? So that is basically purpose what we want to do. So how we can improve to the every point, then you need to have a more definition. So I'm going to show you some other definitions, right? So now we see it's oscillating sequence, right? So now we give a sequence of complex numbers. We say C is an oscillating sequence. If for every theta from 0 to 1, then this limit of n to 0, 1 of n, summation n equals 1 to Cn e 2 pi. That means the mean of this Cn, well, Cn is a sequence, right? Not a function. So so that really means Cn C e 2 pi theta that equals 0 mean. So then definitely I need a control condition. That's actually we defined in our paper in the 2018. Then again, the Davenport's theorem said Mobius function is an example, right? Mobius function example. So right. So okay. So now that means I try to define a more general sequence, oscillating sequence, right? So also this one included Mobius function as an example, right? As an example, and then so then you can see some example about the oscillating sequence, right? So then the E 2 pi in alpha, that's not oscillating because if you take a E 2 pi I 1 minus theta, right? 1 minus alpha, right? If you put this together, that will be not equal 0 because this one time that equals 1, right? Equals 1. Summation 1 into the capital N divided N is always 1, so that's not. So this one is not an oscillating sequence. But then you take this like this, then that is oscillating sequence. But also you take E to 2 pi I n square alpha, right? Then that is oscillating sequence. But I want you to remember this one because I'm going to use that one later too, right? So this one is, oh, now this one is not alpha, is not this one. I'm say this one. This one is. So this alpha is rational, that's not. But the alpha is irrational, it is an oscillating sequence. So I want to remember this one, but later I want to say this one is oscillating, but not oscillating of order 2. Not oscillating order 2. So this is oscillating, but not oscillating order 2, right? So later I want you
What's the what? I'm sorry. What's the order? I must have missed that. What's the order? You say
No, I haven't
oscillating.
defined yet. I haven't defined yet. I'm going to define later.
Okay.
I just mention that because I want to remember this sequence. That's not oscillating, but not oscillating order 2. Later, I will define. Okay. Okay. So now, so also I just have another definition, but the first definition actually implies this one. So I want to say this one is oscillating in arithmetic. That really means if you do not take a hollow sum, you take the sum on all the n which equals r mod q, right? That's actually a smaller number of sum, right? So, but still tend to 0. So that actually the first one implies that one actually. So, but I want a separate definition because the reason is for later when I talk about the high order, I have also need to separate them. Okay. Okay. Let's see. So now then you can define the more general linear disjointness, right? You can define linear disjointness. So suppose f is a piecewise continuous function, a piecewise continuous map from a compact metric space X into itself. Then for every complex continuous function and any X, we call this one as observation, right? That's really since observation. If you look at the in dynamic system, you look at the point, right? X. Then you just go to the orbit, right? You get the orbit, Fnx, right? Then the phi really means observation, right? As for example, you temperature or pressure, so on, right? So is usually in physics we call the observation. So now we say a sequence of a complex number is linearly disjoint from f if that is this limit equals 0, right? So for all the phi and all the x, right? So okay, so that is a definition about the linear disjointness. So now I come to the dynamical system. That those terminologies really in the dynamical system, but I will not go very details because if you're interested, I can talk more. But since those are just technical words in dynamic system, but I try to explain what that means, right? So now there's something. So remember, you have an echo-continuous one, right? But now we have a little bit larger than echo-continuous. Echo-continuous is so-called mean L stable. That's actually used by former Soviet Union mathematician Foreman. So I don't know, he used this L means Lyapunov. Lyapunov also is another mathematician. Okay, so Lyapunov, this L means Lyapunov. So what that said? That said, for every epsilon bigger than 0, then there is a delta, such that as long as the distance between x, y is less than delta, then orbit is still less than epsilon for all the integers, but except for subset of natural number. But this natural number set, a subset of natural number has density less than epsilon. So that means this one is almost, when I say almost, it's not really accurate. So it's except the E, that's also echo-continuous. But on the E could be very crazy, right? Could be very large or whatever you can have. But the point is this density of E in the natural number is less than epsilon. So density is defined like this, right? So that means for any n, you count how many points in the E from 1 to 10, you take a superlimit, right? So that is called mean L, MLS. I call the MLS, right? Mean L stable. So that means almost echo-continuous, except the subset which has density small, right? So that is, so now we also define something called minimal mean else stable. So that what is the minimal set? That's another very important concept in dynamic system. So if a subset in X is said to be minimal, that means it doesn't matter which point you pick up, you iterate it, then you take a closure, that will be how the K. Doesn't matter which point you started. So that's called the minimal. So that is also another word called a quotient simpler in dynamic system. So if a dynamic system is minimal, also is not supposed to be not very complicated, but again, there's many different structures there, so still can be very complicated. so minimal is another another way to see a dynamic system can be simpler, right? So now we see this, we see F is minimal MLS. That means if that F restricts on any minimal subset of X, that is MLS, right? So that is one definition. So another definition is called a minimal mean attractability. So, okay, so first, let's say what is the attractor, right? So in dynamic system, we usually call the attractor, that means if you have a big set, you have some small set, that is K. So every point here and the iteration will be attracted to this set. Then this set we call the attractor. So that is called an attractor in dynamic system. But what I'm trying to define is a different way to see how do you attract every point. That means I do this way. So suppose I have this set X. So I have a K here. So now for every X here, then I can find also for every epsilon, I can find Z. So that means if you look at the Z orbit, right, that will be inside the K. Then you look at the X orbit, then that will be close to the orbit of Z, but in the mean way, that means in average way, not every point. Some point could be very far, some point very close, but if you average it, that's still close. So this we call the mean attractability, a mean attractor. So K is called mean attractor, so called mean attractor. Right, that's a different from the so-called attractor in dynamic system. So now if mean attractor, then you have basin. That means every point attract to this minimum set. Then you have another minimum set. You also have a lot of set attract to that. So this one is called a basin. You set a point which is meanly attract to the K. And if X can be decomposited into this basin, so then we call the minimal mean attractable map, right? So that this union could be uncountably, right? Could be uncountably. So this union not only countable, could be uncountably. So so now the theorem we see that really is a theorem in this direction. We first proved is that is published in the ergodic theory on dynamic systems that okay, any oscillating sequence is linearly disjoint from MMA, MMLS flow. Precisely that means this one, right? I just have a definition. Also limit on H minimum set is uniform. So that is actually is one thing said, okay, oscillating sequence.
Just a second. You're assuming both conditions, right? That is to say, you're assuming both MMA and
MMA and MMS, yes.
At the same time. Yeah, it's not either or, it's both.
Right.
Okay.
And yeah, not or, and. Right. Thank you. Yeah. Okay. So that is one thing. Okay, let's see what is that theorem applied. So then definitely this MMA and ML's dynamic system has zero entropy, right? So now since this Morphius function is oscillating, right? Then that implies the Sarnak conjecture hold for this flow, right? I really want to use flow. Right, all the flows. Okay, so actually, for this kind, for example, a lot of people, I just list many other people also studied on the Sarnak conjecture along this direction, but they are directly study Sarnak conjecture, not really try to compare the oscillating and the level of this system. So also I want to say, because the flow. Okay, so that is one thing. That means you use this way, you can check a large class of which is contains the equicontinuous flow, but still Sarnak conjecture is held on this class of flows. Okay, so then I just want to mention that the example I just mentioned before, right? The circle homomorphism, which is called a down-draw counterexample, right? It's a circle we insert every point on the orbit with the interval, then reconstruct the circle, and is the. So then all the down-draw counterexample actually are MMS and MMA, and they are not equicontinuous even on this so-called minimum set. So actually, down-draw counterexample, you have one minimum set, maybe not only one, they have some minimum set, but on the minimum set it is not equicontinuous, not equicontinuous. So that is one example. Another example, so-called semi-adding machine. So this one is I try to explain that. Okay, so adding machine, we know it's adding machine on the. So you have a sigma 2, right? Sigma 2. So every point on sigma 2 is you can write as write as V, right? As I1, I2, I3, right? So what is adding machine? Adding machine of V is like this. It's you plus 1, right? If the I if I0 equals 0, so then I0 plus 1 equals 1, right? If I0 equals 1, I0 plus 1 will be equal 0, 1. Then this one will be added on the 2, I2. You keep doing, right? That's called adding machine, right? Or called odd meter. So so that is so now so the adding machine is equicontinuous. Okay, adding machine is equicontinuous map. Okay, that's another equicontinuous map, so-called adding machine. So that's so. But now you can construct the continuous map, which is so again called the semi-conjugate to the adding machine. But that is not equicontinuous. But that is still MMS and MMA. So that's another example we construct, which is not equicontinuous, but it's still MMS and MMA. So that's in this paper. It's also 2018. So where that's so now you come question is okay. You know the Morphius function is oscillating order 1. I call order 1, right? So now how about the other zero entropy flows, right? So there's another so-called alpha T2 to T2, right? Then there's an integer matrix 1, 0, 1, 1 plus some alpha not equal 0. Alpha is between 0 and 1. So then remember, I just mentioned this one is oscillating sequence, right? This one is oscillating sequence. Remember, I just said before, right? But this one is not linearly disjoint with this flow, right? So that implies this one is not MMS and MMA, but it still has zero entropy, right? This one has zero entropy, but it's not MMS and MMA, right? So then you want to say, okay, definitely the oscillating of a property on the Morphius function order 1 is not enough to study this in this direction. So okay, so I think Mel, I have one.
Yeah, no, go on. Keep, you have,
1 hour and 30 minutes, right? 1 hour. Okay. Okay, I just keep going, right? Okay. So now I have this oscillating sequence of a high order. That's you ask, right? Now what is the oscillating of high order? So now we call the sequence of the complex number is also of order D. If that one, this one, but now you replace this one as 2 pi I Pn. Pn is a polynomial, real coefficient polynomial of degree less than or equal than D, right? Then plus some control condition. Okay. So that's in the 1960s said this Mobius function is an example of oscillating sequence of order D. Okay. Right, so that that's interesting, right? So now I define something called the oscillating sequence of order D in arithmetic. So again, that is take a summation which is smaller, right? Order n equals r modulo q for every r, right? Every integer or less than q. So in order one, I know the first one can be implied second one, but in high order, I didn't really seriously think about this one can be implied that, but I'm not sure yet. but order 1 I can do that, but order 2 I'm not sure yet. So but anyway, so I didn't really spend time to prove it. But I just put it into 2 separate definitions, right? So again, this Mobius function is example. Okay. So now let's say then there used to be a question said, okay, do you have other sequence except this Mobius function or like other arithmetic function which has this kind of high order oscillating? So that's has been the open question for sometimes, but now it's not open now. So that then in the paper with this Akiyami, we actually found some other high order oscillating sequence, which is in view of dynamical system. This is actually called a beta expansion. So that's if you really want to see that's this one, right? If you really say the G equals 1, alpha equals 1, that's a beta expansion, right? You take a beta bigger than 1, you say to the power n and model 1. That actually is so this one has a positive entropy. Okay, this one still have a positive.
This is an almost always result. Do you know it for particular values of alpha and beta?
No.
Okay.
That's almost every beta. I'm not sure which beta exactly have that.
Yeah, famous open questions I think are hiding. Yes.
Yes. That's a good question, right? That's for Mobius function, we know exactly the function, right? For this one, we know almost everyone. But for example, like a Peso number or some other number is or not, that's still questions. Okay. So, but anyway, so you do have tons of this oscillating sequence of high order, right? So, but okay. So that's a good question. That's different between this ergodic theory and the number theory. You really want to know which one is, right? But we know, we usually say, okay, AE, we are very happy. Okay, so that is one result. But then I try to compare this high order with torus map, right? So now we consider a torus map. So torus you can think as lattice in RD, right? D torus you can think lattice in RD. So now you take an integer matrix, project to the torus, get an alpha map. So if the alpha equals 0, that's automorphism, right? But alpha is not equal to 0. But automorphism usually is continuous. But if you plus the one I just mentioned, this one is not equicontinuous. This one is not equicontinuous, okay? But still have an entropy 0. But if alpha equals 0, that's equicontinuous. Okay, so now I'm going to define something called okay, first let me, because next slide I will show you what is all the entropy 0 towards alpha map. But at this moment, I just want to say, maybe I should show you another. Okay, so let's see, what is all the 0 entropy alpha maps on D torus? So in case this TA has 0 entropy, then you must have all the eigenvalue for this matrix must be has absolute value 1, right? That's actually due to Sarnak a long time ago. Then if from a chronic, this actually not only have an absolute 1, it must be is so-called root of unity. So that means after you do some k iterate, that all the eigenvalue becomes 1. So now I define, actually here's not I define, so that's people in this direction called so-called distal. So usually distal has not equal 0, but I just include all the a equals 0 too. It doesn't matter. So then I said, okay, if a has all the eigenvalue 1, we call this distal. If a not equal 0, that's really distal. That's actually not equicontinuous, right? That's every point you can eventually go away. So that's really means that. So if that is all the eigenvalue is 1, then I show the result said, okay, if any oscillating sequence of order D exactly is matched, is linearly disjoint with torus map of D torus, that's distal. But then I just mentioned that before, right? So you have this 0 entropy, you iterate k times becomes distal. So then any oscillating sequence of order D in arithmetic is linearly disjoint with any 0 entropy alpha map of D torus. So that basically solve this entropy 0 alpha map. I think for the dimension D equals 2 and D equals 3, a lot of people already started that before, but I try to get all the D. But that show that's actually not very difficult. So then again, you want to study some so-called nonlinear screw product. So usually here is x, y. I'm showing you on the D torus, you get a map is x plus alpha. But here is y plus h of x. H is a continuous map. So that's we call the screw product. For screw product, H is analytic. Actually, Sarnak and another people also 01 already started this one. Show this one is linearly disjoint with Mobius function. But in general, H is continuous, only continuous function. That's still open question. But another important thing is how about for high torus, right? D is bigger than equal than 2, right? D is bigger than 2 or bigger than 3. So is that true or not? So that basically is still open for all the continuous H. So, but H equals 0, that's actually the alpha map, right? So, but anyway, so there's still a lot of things to do. So now I just want this slide said, okay, Sarnak conjecture is how this entropy 0 alpha and D torus. So I will see this. A lot of people really did a study in this direction, including Sarnak himself and his co-author. But anyway, a lot of people. So okay. So then there's another question. Actually, is that only high order is enough or not, right? But unfortunately, recently this guy, Abdoué, he wrote a paper. He actually showed that he can find a sequence of all the order D, but it's not linearly disjoint with entropy zero flow. Where this theorem, this result really depends on this Theorem sequence. So that is a Theorem sequence. I think everybody know, probably know. If it doesn't matter, let me just say what is a Theorem, right? You take 0, then you just flip the 0 to 1. So you put 1 here. Then you just convert it, right? To convert it, then you get 1, 0, right? That means 0, 1. The bar means 0, 1. No,
1, 0.
1, 0, sorry, 1, 0. Then you bar here, right? Then you bar here, the 1, 0, 0. Then you get a 1, 0, 0, 1, right? Then you keep doing, right? So that's the Morse sequence. That's the important sequence in information theorem, right? So this one actually has 0 entropy. So that's a Gross number. The Gross number of this one is polynomial. So you have a 0 entropy. So then in this paper is in archive. I'm not sure this one published already or not, but he actually calculated this Gauss norm. So he actually calculated the Gauss norm is actually like this, asymptotic like n to the minus c. So that means that you eventually you have a very small Gauss norm. Then in his paper, actually, he used this result to show this Morse sequence is actually high order of order D for every D. So that is actually interesting. That's different from a Mobius function and from a example we constructed. This one has entropy 0, still is a high order. That's another interesting thing, different from what we did. So now, okay, this one itself has entropy 0. Also, is also reading. Then you couple this itself. That's not a linearly disjoint, right? Just like a e to the 2 pi theta, right? You couple with itself that will not be linearly disjoint. So then this one actually is one example, right? So then so actually that is an interesting thing. So I spell wrong here. So that is a recent thing. Actually, okay. So now there's another interesting thing. A very interesting thing is actually so-called correlation. In dynamic system, we call the correlation means the two things we correlate together, right? And eventually will be go down to 0. That's called the decay of correlation. So then this Bogan, Sarnak, and Ziegel in the very beginning of this conjecture formulated, they actually show that if given 2 arithmetic functions, both but this condition I think you can replace by this control condition I just mentioned. So that is not very important, I think. But and mu is multiplicative, right? Multiplicative. So then, if you for any pair of distinct prime number p and q, then you have this kind of correlation. Then that will be implies this linear disjointness, right? It doesn't matter if function is a Mobius function or other function, as long as that is multiplicative, right? So that is have another thing is this called Euler conjecture and decay of multi-correlation, right? So that's the Euler conjecture. I think is a very old conjecture in the number theory, right? That side, this side is if you take any choice of sequence, as long as you not make this is all equals 1, then this multi correlation is as mean is 0. That's a multi correlation decay of that's called a decay of multi correlations. But I'm going to use the word is really in the dynamic system that maybe in the number theory is not really use this word. But okay, so then very recently study, actually, that's what I'm trying to still understanding with some student too. Try understanding this one. So first, you can similar define something called a Euler sequence, right? You can take any sequence of complex number, as long as you have this decay of multi-correlation, then we call the Euler sequence. Then now we still don't know the Möbius function is this Euler sequence or not, right? But the point is you still can use a similar construction I just mentioned before to construct some in dynamics point of view, that's a Euler sequence.
But
then,
again, this would be a for almost all beta rather than a particular beta, right? Another almost all construction, yeah.
Yes, right. If I can, if you can find a concrete beta, that would be great. Okay, that would be great. So in particular, you know, in number theory, you have a lot of some kind of numbers called the Pearson number or some number, you know. See, you can try see that is true or not, right? That's actually a very interesting open question, right? Right. So now that's my last slide. I will say that what is the relation between Euler conjecture and Sarnak conjecture, right? So first, Euler conjecture actually implies this Sarnak conjecture because that's correlation implies this linear disjointness. But then most interesting work recently actually made by Witch and Terrace Tao. So then in this paper he actually, but this paper is not published yet. So I'm still trying to study this paper yet. So this one said, okay, you combine these two results together, you can really say Sarnak conjecture implies Euler conjecture. So someone said, okay, that should be true, but for me, I still try to understand in this one. So then that means this Euler conjecture and the Sarnak conjecture is really equivalent. That's why we are interested in this conjecture too, right? Okay, so then that's I think that's my last slide.
Great.
Thank you.
Thank you very much. Are there questions for our speaker?
Okay.
Yeah, I have two questions, which may be peripheral. One, has anyone calculated the zeta function of the Möbius flow, and how does it differ from the reciprocal of the Riemann Zeta function? And secondly, what's the minimal information that one needs about the Möbius function to actually make the results work for more general, the Möbius functions? For example, the one that results when I take the reciprocal of the Dedekind zeta function of a number field. I get a Dirichlet series where the coefficients are also plus and minus one, and one gets basically a flow, as you indicated. So right. Are these the things known?
No, so first for your first question, right? So that's also I want I really want to also search. I'm not sure I have the answer for that one, because Möbius flow somehow really related with Riemann hypothesis, but in which way I'm not sure yet. Maybe someone else knows. Yeah. But the second one is that we try to find the order probably really is try to understand how this order behind this Möbius function can be applied. Yeah.
Let me ask you a third question. If I have the zeta function of a dynamical system, where do I read the entropy? Does it appear as somewhere as
oh, you mean right for the my share is gone already. So you mean for entropy have a lot of book to read. So there's a paper, if you want I can send you the C9 paper. Well, let me see if I have that right. C9. Oh, I'm already out of sharing. So let me just say this. So actually, there's a paper which is called the ergodic property of square-free numbers, made
Okay.
by Sinai and his student. This one has a lot of information how to calculate the entropy for this square-free
Oh,
flow.
okay.
Yeah, but I'm not sure.
All
I
right.
can,
Thank you.
I'm not sharing now, so I bet. Yeah.
Other questions? Very interesting. Very nice.
Do these results relate to questions of random distributions? For example, the question of whether 3/2 to the end is modulo 1 is random. Would all this theory bear on that?
Right, but actually, you see, there's a Moses function is random, right? So, okay, for first, if you look at the Rich's result, right? So, if you have a Mobius flow, right? So, what is a Mobius flow? Is actually is not a has entropy positive. That means the Mobius flow has a lot of expansions, basically, right? So then there's we know the topological entropy is bigger than 0. But then this topological entropy is actually a global measure of complexity. It's not a macro measure of complexity. Then you must have something called a measurable, or called a measure theoretical entropy for every invariant measure. So now you want to study what's the invariant measure of the Mobius flow, right? So you want to study something good invariant measure. That's Rich's work. So actually, he found out this so-called admissible measure on the Mobius flow. Actually, I shouldn't really say it on Mobius flow. At this moment, they found an admissible measure called the invariant measure on the bigger than space bigger than the Mobius flow. But conjecture is that one is the same like a Mobius flow. So if you for this measure, if you can calculate something called a measure theoretical entropy, that will be the macro way about the complexity or randomness.
Other questions, comments? No one wants to prove 3/2 to the end is uniformly distributed today?
So.
Oh, yeah. So thank you very much.
Let me ask you a question if I.
You have quite, I think Carlos has a question, right? Carlos, you want to say something?
Yeah, in one of your definitions, you had the number n running through arithmetic progression. So my question was whether instead of that condition, one could put in the coefficient, say just a character, chi-n, let's say a multiplicative character, modulo d, and so track basically the same type of information.
Maybe, I'm not sure. I'm not sure, yeah. Maybe, I don't know.
Okay, all right, very interesting, yeah.
Thank you.
Okay, great. So we have a little, obviously it's a CUNY mini series. So next week, our speaker is Guy Moshkowitz from Baruch, who is going to give the second part of talk following Alex Cohen on tensor rank of matrices well, tensor rank. Choose your favorite tensor rank and show they're comparable. Okay, Kevin, before you go, Brian.
Yes.
You raised your eyebrows a little bit when I said that the PhD students at Columbia are demanding a minimum $45,000 a year fellowship amount.
45?
Yes. So my daughter called me a little while ago and reminded me or told me that in 2014, the graduate students at NYU unionized. And in 2014, they got a minimum fellowship of $36,000 for all PhD students in the arts and sciences.
Mhm.
And I think at CUNY, the most we give is about 25,000. But
Right. I remember that. Yeah, we are very low actually.
yeah, but really, if places are giving, in the high 30s, low 40s, that really is not competitive if you are trying to get a graduate student that someone else wants to get.
Yeah, more power to them. I was surprised by the number, but it wasn't a judgmental eyebrow raising.
Yeah, no. I mean, it struck me as very high too. And I was kind of surprised when my daughter told me that 7 years ago, the minimum at NYU was 36,000. And every PhD student admitted got a fellowship.
I'm pretty sure we have assistant professors at CUNY who aren't making 45,000. What's
I don't
the
think so.
what's the bottom of the pay scale?
It's above that.
Yeah, something like that.
It's probably around 60, it's in the 60s, I think.
Huh?
I mean, I haven't looked at the salary schedule for a decade or two. But of course, it doesn't matter to us, right? I mean, there's no notion of merit or anything else in the CUNY system. So
The bottom of the pay scale is low, as Kevin said, but I don't think they offer anyone that kind of salary.
And maybe
Right.
maybe you should, maybe Mel, you maybe should talk to Ara like him talk to our provost.
I don't think that will help.
The bottom for assistant professors is 52,000.
Right. What's the top?
For who? For full
Assistant
professors?
professors.
No, assistant professor.
Assistant professors, it goes up to 99.5.
Right. Okay. So
So this is slightly in the future.
it used to be said at Lehman that I raised faculty salaries more than the union ever did, because they had the policy that assistant professors had to be hired at the bottom step. And when I became provost, I observed that that's what they did, but it wasn't a requirement. So I started hiring people at higher steps because I had the authority to do that. And the only people who were upset were people who had been hired a year or two before I came to Lehman, because they didn't like the fact that a new assistant professor was getting paid more than they were getting paid, even though it wasn't coming out of their salary, right? I mean, it's like they were like disjoint events, but psychologically it rubbed them the wrong way. But so even though I could start people at a higher step, I did not have the authority to raise someone's step once they were in the system. That is extremely difficult to do. These had been extremely difficult to do at CUNY. But what can you do?
So the union should have tackled that.
Well, the problem with that is that it